All right, we want to talk about our total energy expenditure, our calories. How do we measure that, and how do we know how many calories we're burning? And there's two different ways to do that. There's direct calorimetry and indirect calorimetry. Let's first talk about what is accounting for all of this energy expenditure anyways. And we can do this, for total energy expenditure, we would do TEE. So there's a little equation with this, right? So TE is going to include everything, and that's going to include your RMR. And your RMR is the resting metabolic rate, and that's pretty much what you are, just a rest to keep your organs alive and everything. It's a little bit different than BMR, which is under a very strict set of conditions, like laboratory conditions. So your RMR is about 5 to 10% higher than your RMR is. And then you have your TEF, and that is the thermic effect of food, or thermic effect of feeding, basically. And this is, when you metabolize foods, especially like proteins and things, you give off heat, and so there's going to be some energy with that. And then, speaking of eating, that's the other one, and it's EAT. What does that stand for? Stands for exercise activity thermogenesis, right? When you exercise, you're obviously going to be burning more calories. So exercise activity thermogenesis. And that's a neat thing to do. Speaking of neat, look at this. NEAT. Neat. That's actually non-exercise activity thermogenesis. And this makes up a really important one, because this is the times when you are just, you're sitting down and you're tapping your foot, you're fidgeting, you're moving. Here I am talking to you and I'm moving my arms a lot. I'm not exercising per se, right? But this is the non-exercise activity thermogenesis. And it accounts for a lot of things. So the RMR is around like 60 to 70% of our total TEE, versus the TEF is only around 10% or so. And then the EAT, that's going to make the biggest deal, because of course, if you're, if it can make it be a really big deal for things that are not just normally part, right? If this is 60% or so. Exercise can contribute quite a bit if you are very active. And then, of course, your NEAT. Those two together can be like 20 to 30% of everything. Now, your muscle, it's interesting to consider, all right? So your muscle, we know that this is per day. So let's say you have a kilogram, 1 kilogram of muscle. How many calories are you going to be burning per day with that? It's around, we'll just say about 13 kilocalories per day. And versus if we look at adipose tissue, okay, AT for adipose tissue, let's do a kilogram of that. Well, what is adipose tissue going to do, right? I mean, that's not doing contraction and everything. That's not going to be a lot. That's only going to be around 4.5 kilocalories per day. And this is a rest, all right? Now, if you're contracting muscles, well, okay, so this here was at rest, but so during activity, okay, this could be, 50 to well over 100 kcals per hour, right? It could be even higher than that. It depends on what muscle we're talking about, and that's per kilogram. So all of a sudden, your skeletal muscle, it can start burning a lot of calories per day, but whereas the adipose tissue, only 4.5 kcals per day, and it's not going to get like all metabolically active and everything, all right? So how do we actually measure this? And we do that with this calorimetry, all right? This is the idea with calorimetry. And there's two different ways to do it, right? There's direct calorimetry. It's like DC, direct current. And indirect calorimetry, all right, IC. And the direct calorimetry, again, this is really all about actually measuring the amount of energy and heat that's being produced. And it's all about the thermodynamics, right? Because it's the energy you take in is the energy out. So this is calories in, calories out. Really, that is what calories mean. In fact, if we look at this, calories, okay, so we have a calorie is equal to, basically it's how much energy is required to increase a gram of water, a gram of H2O, to increase that 1 degree centigrade. All right, that's what a calorie represents. And the calorie, notice it's a little c actually. So typically one c right there, so 1 calorie, we often we'll often write, and you see it over here, I wrote kcal. Okay, so kcal would be equal to, so 1 kcal would be equal to 1,000 of these calories. And, or another way to just do that is write 1 big C, 1 calorie that way. I like to just write kcal because that's typically what we do, like in thermodynamics and chemistry, is just kcal. But on your food labels, you'll see written with a big C for kcals. And now when we measure direct calorimetry, what we're doing is we basically put you in a chamber and then we measure all the heat that is produced. And so it's extremely laboratory tight conditions, and we can measure changes in the smallest changes in temperature. And that's going to give us how much heat was produced and therefore tell us how much energy was expended because, again, energy in, energy out. It's thermodynamics, calories in, calories out. And we can do that very accurately. It's very impressive. And so this really cuts to some of the myths out there about, people's, different metabolisms and, like they eat these calories and that calories. It always comes back to thermodynamics. Now, I will say, although calories in, calories out is true, it's also true that the body is different, and 1 calorie of some foods are not the same, don't have the same metabolic effects as a calorie of a different food. For example, even in this equation right here, we have TEF, that's a thermic effect of food or feeding. Well, that alone tells you that there's going to be something different about the calories that we're ingesting, and that's where some of the differences come in. But again, it is thermodynamics, right? Calories in, calories out. So what about with the indirect method? What does that really tell us, and how do we use that? So indirect calorimetry, let's talk about this. So with indirect calorimetry, we want, this is going to be done with gas analysis, all right? And for the two things gas analysis, we're going to figure out what is the VO2, okay, the volume of oxygen consumed. And we're also going to be looking at, another one is the CO2, or the VCO₂, the volume of carbon dioxide consumed. And the reason why this is important and what we can know from this is because it tells us 2 critical things. It tells us how many calories are actually being, or how much food is actually being consumed, because we're literally measuring the amount of oxygen being consumed. We remember from complex 4 of the mitochondria that oxygen is there, comes in and literally combines with the electrons and hydrogen ions to create water. So oxygen is literally being consumed, and then the TCA cycle, CO2 is literally being produced. So this tells us how much oxygen is being consumed and into the foods, right, to make water, as well as how much CO2 is being produced will tell us what type of substrate. Was it carbohydrates or was it fat that was being produced? So this together, these 2 things together are going to tell us what is known as the RQ value. Okay, the RQ value is essentially this math here. This is the VCO₂ over the VO2. And if we do this math, just basically looking at from the cellular level, all right, with this pure stoichiometry. Let's look at carbohydrates with glucose. Okay, so if we have glucose right here, we remember it's C6H12 6 plus, we calculated 6 moles of oxygen will be needed to combust a mole of glucose, and that'll make 6 CO2 plus some water, right? And now we can do this math here, right? If we do the exact same thing, we could do our 6 CO2 and our 6 O2, and that's going to equal 1. So we have an RQ value of 1. Now we can do the exact same thing with, say, our fatty acids. So we can take something like palmitic acid, and we can do this math. So this is carbs, this is fat. So C32 C16H32 O2 plus. So this was going to take 23 O2 molecules, and now we can make 16 CO2 molecules plus, depends on how we're going to calculate this. We'll say 46 H2O because of 23 water molecules. But the important thing here is, so we have the 23 oxygens, and we make 16 CO2s. So we can do the same math here. So we'll just do 16 CO2 here over 23 O2 here, and so 16 divided by 23 is going to give us 0.7. So that's the RQ value, right? That's the quotient, the respiratory quotient, basically. So with carbohydrates, it's 1, whereas with fats, it's going to be 0.7. And so because we can measure the volume of oxygen being consumed and the volume of carbon dioxide that's being produced, we can tell you what substrate you're actually going to be metabolizing primarily, right? Now, in a mixed diet, right, because people have a mixed diet, not just carbohydrates or fat, and plus there's protein as well, you're going to have around 0.82, right, for a mixed diet. We'll say normal. And again, it depends, because if somebody's like on a ketogenic diet, they're going to be much closer to the 0.7 versus everything is just super high in carbohydrates. They'll be a little bit higher than that. Because we're talking about the mitochondria, what's happening in the mitochondria, this could also maybe indicate how their mitochondria is functioning, right? Is it burning? Like when you're just at rest, you should be close to 0.82. But if you are totally at rest and yet your RQ value is really high, like closer to 1, it could potentially indicate that your mitochondria is, for whatever reason, primarily burning glucose over fatty acids, and that could be something to look at, right? Maybe kind of like an indicator of something going on. I didn't really put protein here, though, because protein is not just one molecular formula, right? There's a lot of different protein size, peptides, the amino acids. But typically with proteins, for example, they're going to be around 0.85, the RQ value or so. All right. Okay, so the other thing is with the oxygen. As I said, oxygen is being consumed by the mitochondria. And here's the equation right here: what one mole of glucose plus a mole of 6 moles of oxygen. So we can actually calculate exactly like how many grams or how many calories each gram of carbohydrate is, as well as how much oxygen that gram is basically going to consume. So with the carbohydrates, you typically have this, you'll say that the enthalpy of reaction here is going to be around 670 kcals, okay? 670 kcals per mole. And so you have a mole of glucose, you get 670 kcals. So let's just come over here. We'll do this here. So do 670 kcals, and if we divide this by the molar mass of glucose, right? So you can add this up, and you get about 180 grams per mole, right? And this is also per mole, kcals per mole. So moles will cancel out. And so 670 divided by 180 grams, right? And that's gonna tell you basically how many grams of calories, so how many calories every gram of carbohydrate is. And this is about 3.7 kcals per gram, right? And we often round this to say about 4 calories per gram, right? You've seen that, carbohydrates are about 4 calories per gram. And that's because different carbohydrates are different, right? Like if it's a dextrose or sucrose, there's little things that change certain steps in the pathway. So we round it to about 4 kcals, because some could be a little bit higher than that. So on average, carbohydrates are around 4 kcals per gram. And then we can do the exact same thing with palmitic acid, just as a fatty acid in general, right? So let's say with the fatty acid, this is going to be like 2,397 kcals. Okay, so we just do 2,397 kcals per gram, and then the molar mass of, if we use palmitic acid, for example, 256.4 or so, 256.4 grams per mole. And we do this calculation, and we end up getting somewhere around 9.3 kcals. So, and we can just round that. We'll just say 9 kcals per gram. Right? So that's how we know where how much calories are in each gram of carbohydrates or fats that we're taking. Now, the other thing that's interesting is we can figure out, okay, how many liters of oxygen gas is actually being consumed for each one of these. And to do this, we can actually take the 670 kcals. So let's do this over here again. All right, so we do 670 kcals. This is per mole of glucose, right? So per mole of glucose. And we can, we know how many moles of oxygen there was. There's 6, right? So there's 6 moles of oxygen. So we just do some basic stoichiometry. So you divide this by 6 O2 moles, right? 6 moles of O2, and that's going to be 1 mole of glucose. So moles cancel out. If we take 670, divide that by 6, all right, we'll just do, it's about 111.7 kcals per mole of O2. And now using our DL gas law, PV equals nRT, we know that there's about 22.4 liters of dry gas. I guess that's STB, but that's the one we use of oxygen. So if you have one mole of oxygen, 1 mole, so of O2, divide that by 22.4 liters of O2, and you would get 4.99. So we'll just say 5 liters, or sorry, 5 kcals, 5 kcals per liter of O2. In other words, with 1 liter of oxygen, you are burning about 5 kcals of glucose, of this substrate. All right? That's how this number comes from. That's why we get 5 and like 5.05 or something. But when you do the mix with all the other carbohydrates, as we talked about earlier. So we'll say 5 kcals per liter of oxygen consumed. Now, we actually want to do the exact same thing for palmitic acid. And so if we have, let's see, we use this number right here. Let's just do it down here. So we'll go 2397 kcals per, no, let's see, this is 2397, oh yeah, it's per gram, so this is per mole, right? Per mole. And do the exact same thing we did here. Divide this by 23 oxygens, 23 O2, and this will tell us how many kcals we actually got for each, how many kcals we got for each mole of oxygen. So 2397 divided by 23 ends up being around 104 kcals. 104 kcals per mole. And now if we just take this number, divide it by 22.4, gives us about 4.7 kcals per liter of O2. Okay, now this will be important here in a little bit, but I want to show you exactly why we have around 5 kcals per liter of oxygen for glucose versus around 4.7 kcals per liter of oxygen for fats. And that's going to make a little bit of some difference when we start looking at the respiratory quotient, all right? Now, about this respiratory quotient, this is all basically what's happening in the cell at the cellular level, like this actual metabolism happens in the cell. And this is based on just stoichiometry, right? Just based on just mathematically what we did. Now, in practice, we don't really get to measure what's directly happening in the cell. Rather, we're measuring something called RER. Okay, so this RER just stands for respiratory exchange ratio. And it's pretty close to the RQ value at rest, okay? So at rest, or I'll put here SS for steady state, okay? So at rest or steady state, the RER is pretty close to the RQ value. And so we can use RER in the laboratory, like in practice we can. So we can actually put a mask, and of course many of you have done this before, put the respiratory mask on, not respiratory mask, but the mask on, and you can measure how much oxygen you are consuming, and then you can measure the amount of CO2 that's being produced, and then you can, so you'll get VO2, and then by knowing the volume of CO2 being produced, you can calculate what the RER is. And when you know what the RER is, then you can figure out what is the percent coming from fats or carbohydrates, right? So this is going to be an important thing because, again, the RER tells us what percent is coming from the fat, as well as how much being consumed, how many kcals are being consumed per liter of oxygen. Now you can either look that up in a table, or you can actually calculate that. So let's do a calculation so you can see. If you did let's say you did an RER of 0.82, right? So you had a kind of a mixed diet, right? Like a normal diet is 0.82, right? So you had some carbohydrates, some fats. You measured both of these values, and you got an RER of 0.82. So we have an RER is equal to 0.82, and we can use this to figure out how many calories are coming from fat, for example. And there's a simple equation to do with this. It's basically you just take 340, and you multiply that by your RER, and then you add 340. So multiply these two together. 340 times, okay, we're using the RER of 0.82, right? And that's going to get, and then add the 340 to that. You end up getting about 61%, right? So 61% comes from fat, which means that 39%, we could just put 39% comes from carbohydrates. And it makes sense that it would be mostly from fat because at rest, 0.82, you're resting, you're not exercising a lot, so most of your metabolism is going to be coming from that fat. And the 0.82 is closer to the 0.7 that we calculated right here, the 0.7, than it is to the 1. So this is kind of a check to make sure when you're doing the math, you can check to make sure it's accurate. So this is how you can estimate that. Then the other thing that I said is you can also estimate, well, how many, what exactly is the kcals per liter of oxygen being consumed? Because again, with carbohydrates, it's just over 5, whereas with fats, it's 4.7. So there's slight differences. But I want you to pay attention to the fact that we can measure differences this close. You would think, look, this is technically like 5.05 or whatever, and this is like 4.7. And yet, so these are pretty close. So this is within the tenths place, and yet we can be that precise in measuring with just indirect calorimetry. And so if we can be that precise, we can really calculate and quantify all the calories that you're basically consuming and you're expending, right? So just keep that in mind. But I'll just show you quickly how you can end up calculating how many kcals are being used. And it's so in this case, you would just take your that's not RER equals. I don't want you guys to be confused about that. I was just saying really you're saying the percent of fat is equal to that. And now we're going to say how many kcals per liter of O2 is being consumed. In this case, so we do 0.82. So same idea, we're going to use that same resting one. 0.82, 1.23 in this case, and then multiply that by your RER, and now you add the 3.83 to this one. So plus 3.83. And when you do this, put 0.82 into this one right here, because this is, right, what that one is. Now you can figure out exactly about how many kcals you end up getting. And it's around 4.83 kcals, 4.83 kcals per liter of O2. So with a mixed diet, every liter of oxygen you consume, you are basically burning 4.83 kcals per minute. Now, per minute, because this is actually liters of O2 per minute, which is actually cool because we could actually start asking ourselves questions and calculating things. For example, how many, let's say you ate 250 calorie snack. How many minutes of exercise would you have to do in order to burn that? And let's say you're going to do it at rest, you're going to do jogging, and even maximal exercise, right? So we can actually do that. Let's just move over here and let's just do, so we have a 250 calorie snack, and we're going to figure out how many minutes is it going to take in order to burn this, right? So let's do the first one. We'll do this first one here. Let's do A. We'll do this at rest. How long at rest until we burn that many calories? Well, at resting, you typically, like your rest metabolic rate, just at rest, you're 250, 300 milliliters per minute or so. And so let's just do 0.3 liters. So at 0.3 liters of O2 per minute. That's your resting, how much oxygen you're consuming at rest, right? Your VO2, the volume of oxygen you're consuming at rest. And now you're going to be burning, how many calories do you burn for every liter of oxygen you consume? Well, we have right here, it's going to be between basically 5 to 4.7. So we could figure out, okay, what is the RER? And then we could do this math right here. It's be around 4.83. But let's just make our math easier for the sake of making math easier. And we will just use 5, round it to 5, right? So if we can put here 5 kcals per liter of O2, right? So now our liters of O2 cancel out. And that's going to leave us with kcals per minute, right? So if we take 0.3 times that by 5 and divide it by 1, and you end up getting around 1.5 kcals per minute. So 1.5 kcals per minute. Now, okay, so if we're doing 1.5 kcals per minute, how do we figure out the 250 calorie snack that we took? Well, we can just go 250 divided by 1.5, and that's going to be around 167 minutes. Okay, so 167 minutes, which is essentially what, 2 hours and 47 minutes. There. So you just ate that 250 calorie snack, and now you need to do it at rest. It's going to take you about 2 hours and 47 minutes in order to burn that snack. Okay, so now you're like, okay, well, that's why I'm going to exercise. I got to get rid of this. And so let's do that. Now you're going to go for a jog. And you're jogging now, right? So your oxygen consumption jumps up, quite a bit, 3 times as much. Let's go to now 0. No, let's actually go to just 1. We'll go to 1 liter per minute. Let's make this super easy. And that's typical. It's a good job. Okay, so 1 liter of O2 per minute. And we do the exact same thing. We use 5 kcals per liter of O2. So liters of O2 cancel out, and that means we're getting 5 kcals per minute. And then we can do 250 divided by 5, right? So 250, because that's, again, how much our snack was, 250 divided by 5. And now, how long is that going to be? Around 50 minutes. So it's almost an hour of exercise just because you took that little snack. So you think to yourself, all right, no problem. I'm going to exercise harder. I'm going to go all max effort. Well, let's say that let's say you're going to go, really kind of push it yourself more. So let's say if you're doing 1 liter, let's say for a max, let's do a max effort. No, it's more of a moderate type exercise. So let's say you just do 2 liters per minute. Okay, so 2 liters per minute. Because it depends on your jog too. I mean, this is like a pretty slow jog, I guess. If you're just doing 1 liter a minute of oxygen, that could be like, 3 something miles per hour. So that's not, could be a jog for some people. 3 to 4 miles per hour or so. But let's say you're actually going to jog. So let's actually just change, because if I was just thinking about this, we'll say this is a walk. And now we're going to do a jog. So 2 liters per minute. We do the exact same math, and it's just going to be 25 minutes. Now, let's go to your maximal activity. All right? So now we'll do a full-on run. Let's do a max run, okay? Let's do the hardest run you can, and we'll just make this really easy. We'll go to 4 liters of O2 per minute. Now, this is assuming that you can actually consume 4 liters per minute of O2. This is actually pretty high, what we call VO2 max. This is a maximal exercise. A VO2 max of 4 liters per minute is a trained athlete. That's a pretty good engine. They probably are potentially excellent to superior, even around, if they're 70 kilograms, and they're going to be around, 59, 60 or something. Anyway, it's pretty high. So not everyone's going to be able to do what we're about to calculate here, right? But if we say they can do 4 liters per minute, well, then it's just going to be half that, right? 12.5 minutes. Now, how many of you can run at your all-out, makes your max, not your all-out effort, that's a sprint, but for your max aerobic activity for that full 12.5 minutes? I mean, that's an elite level performance. Your elite level athletes could potentially run at their VO2 max for the full 12.5 minutes. So that makes you maybe start to think a little bit about, what you're going to do with your snacks, right? Because if you think about it, your 250 calorie snack, and that's just like, I don't know, just a handful of, I don't know, a little cookie there, a little muffin, or your cappuccino. It took you, what, 2 minutes to consume that? Versus, almost 3 hours, if you're not exercising, down to 12 and a half minutes of like full on out. Now, it does get worse than that, because we actually know that as you do this extra activity, right, where you're stimulating your EAT, your exercise activity thermogenesis, guess what happens to your NEAT? Your NEAT tends to go down, and so the amount of calories you burned with this exercise could only be, there's an article about 28% was compensated for. It could be even more than that, even 50%. When you exercise hard in the day, you tend to burn less calories throughout the rest of the day, because these other things start to equilibrate, right? Your body's always looking for homeostasis, so you end up not burning as many calories. So again, it's another reason why just doing cardio is not a great way, it's not effective in order to lose weight. It's all about a caloric deficit from eating less. And so if you really want to increase your metabolism, you got to increase your RMR, right? I said the RMR is like 60%, 70% of your TEE. Well, what makes up the RMR? The biggest thing that makes up your RMR is besides like your brain and your vital organs, right? Because those ones that's how it is, and that's going to be like, the majority of it. But your skeletal muscles, okay? Your skeletal muscles is what's making up most of just resting, as well as all the other parts. Your muscles can be part of that. And so as you do weight training and you gain more muscle mass, you can burn a lot more calories, just because you're going to have a higher total resting metabolic rate. And that means that both the EAT and the NEAT are going to potentially be higher as well, depending on what you're doing with your activities. So point is, cardio training, running is not a super effective way to decrease caloric intake, because you can see from the math here, it just doesn't quite add up. But that doesn't mean it's not important. In fact, cardiorespiratory fitness is very important, and it's one of the it's one of the strongest indicators of longevity, because it's going to you're talking about your heart function, your lung function, your mitochondrial density, all of these things. So I'm going to talk about that next, about what VO2 actually is your VO2 max, and why that is such a strong indicator and predictor of overall mortality, chronic diseases, and your entire basically health, right? It's a great metric for your overall health. So, all right, I'll see you guys in a minute.